In this NDT training module, I'm going to look at reliability and probability of detection. And this is in regards to finding flaws in objects that are having testing performed on them. Hopefully, it's not just a roll of the dice, but rather we can have a high enough reliability and high enough probability of detection that we aren't leaving things to chance. So first off, I do want to make an acknowledgement. A lot of the information here, the majority of the information is sourced with permission from presentations by Ika Verkunen, who is a professor and also works for a company called TrueFlaw out of Finland that specializes in NDT reliability and probability of detection. And he presented a very similar presentation to this at the first virtual European Structural Integrity Society Summer School in July of 2022, titled NDT Reliability and Probability of Detection. So what we first need to know about reliability is that information equals the lack of uncertainty. And so we want to have information so that we can eliminate uncertainty in our things. So NDT ultimately seeks to reduce that uncertainty by eliminating or finding any flaws that may be present, which are of a size which is deemed requiring attention. You can actually have very, very small flaws, smaller than what's called a critical threshold, that are acceptable where an object or piece of equipment can be kept in service. We just want to make sure we're able to reliably find those flaws which exceed that threshold. So why does it matter? Why does NDT reliability matter? So we perform NDT to reduce uncertainty in regards to the biggest possible flaw that may be in a given component, as well as the location of the flaws in a component. And if NDT is too uncertain, then the uncertainty for an inspection or an uncertainty about a part is not reduced. And that can be flaws can be missed, or maybe there may be indications made in error known as false positives. What this ultimately means, though, is that unreliable NDT is useless, or often worse than useless, it becomes dangerous. Useless in the form of a waste of time and money, but the dangerous part comes from the false sense of safety or risks that you're putting the individuals at that are using the equipment or traveling on the airplane or other equipment that they're going to be that would have NDT being performed on them. So first we have to ask ourselves, how good is good enough? And what do we mean by that? So there are costs involved with NDT, and it's a balancing act. So the first is the cost of inspection. So inspection includes things like the time required, whether it be downtime or man hours to perform inspection, the equipment needed and materials to do it, the training that the NDT practitioner is given, etc. But keeping in mind that there is no value to look for flaws that are never there, or there is no value to look for flaws that are already known to be there, either are very large or a worn part, for instance. The next two parts of that are the cost of false calls and the cost of remaining misses. So that kind of has to deal with, again, those flaws that are never there, those flaws that are already known. And then high reliability is needed in order to reduce that cost of false calls, because we don't want to be taking objects out of service sooner than when they need to be, than they should. We want to get the full life out of a component or an object. And then cost of remaining misses is those things that we don't find. And particularly in aviation, the cost of remaining misses can be extremely high. This is talking about dangerous situations that could result in the loss of an aircraft and all lives on board. So it only takes one missed flaw that can result in these disastrous consequences. So if you take these three things together, cost of inspection, cost of false calls, and cost of remaining misses, it needs to be less than the cost of misses in absence of NDT. And this isn't to say that we should, this is not a case to not do NDT. It's a case where we have to, we could perform inspections to the point where there would never be any kind of a risk present whatsoever. But in that case, the airplane would stay on the ground 100% of the time, being inspected over and over again, and never actually get a chance to carry any passengers. And so there, that would be too high and compared to doing NDT. So it's a balance there. So NDT fits into the wider industry, and that is uh, from the technician point of view, NDT is being performed on in-service equipment. And this is the current state and any flaws that are present due to the, the conditions that an object is operated under. So this is things like operators, airlines, MROs who perform NDT on the objects. But that information gets fit into a wider industry where it has to be shared with things like engineering teams and OEMs, manufacturers, so that they can do things along the lines of strength analysis. And some of that's done prior to uh, an object or an aircraft going into service, and that is calculating that critical flaw size and growth rates. How much damage is allowed, or how many flaws are allowed. And then material degradation is as objects are in service, the engineering teams need to be able to learn from how that service causes the breakdown of the materials that make up a component, and what kind of failure mechanisms those are, and how quickly they grow, and in what ways they grow. And so data information needs to be transferred back and forth, and then that information that's sent to those manufacturers, engineers, and designers for strength analysis and material degradation, that may have, that often is going to feed back up into making changes or directing the NDT in service over the lifespan of a given product or aircraft or other piece of equipment. So we also have to keep in mind that not all flaws are created equal. And that is the danger, different flaws have different danger levels. And danger presented by a flaw is primarily dependent on its size. That's the main qualifier in most cases. And what that means is smaller flaws are going to provide more time before that flaw reaches that critical threshold. The other part about smaller flaws, they tend to grow more slowly. The growth in most flaws is that are not caused by a one-time event like impact damage, although that can cause further growth down the line. But something like a crack, when it's small, it tends to grow fairly slowly. And a very small flaw puts less additional stress on the undamaged structure. And so that is, it's below, as long as a flaw is very, very small, it may be below a critical threshold. And so while it's in that stage, while it's very small, it's easier to compensate by other means. And the biggest one there is damage tolerant design. There is a certain amount of expectation, a fuselage or a spar or other components are designed in such a way that, if there is some material beginning to fail in a small way, it's not going to instantly cause or immediately cause a catastrophic failure. But NDT is always pushed, and research takes place to find the flaws that are as small as possible. But however, bigger flaws are easier for NDT to detect and NDT to detect reliably. So we have to make sure we find those big flaws, especially those that are right around the critical level. And so NDT has value, it should be performed. NDT is valuable when you need to decrease uncertainty. And decreasing uncertainty is, is to guarantee a certain level of safety. And so NDT can decrease that uncertainty. There is, however, you got to keep in mind, we don't want to do NDT just to do NDT. We don't want to be performing inspections just to say we're performing inspections. They actually have to be providing that decrease of uncertainty. And so that's, those cases are we want to make sure we're not conducting NDT in such a way that it's going to be where flaws will not form in an object or material. So if an object or material isn't being stressed in a way that could cause flaws that would be found by NDT, or if there are already known flaws, accepted, there can be materials that sometimes have accepted levels of impurities or accepted level of known flaws, as long as it's not affecting function or safety, doesn't necessarily mean that that part has to have NDT performed on it regularly. Or if we know that an object or material will be taken out of service before known flaws can be conform. And so that does kind of go back to some of those earlier points where engineers and scientists are studying materials and how they react, and may put a life limit. Although in aerospace and aviation, we've tried to move away from this because we'll talk about later. Even though we know there's going to need to be a margin of safety there, and that means that most parts are going to be taken out of service uh, somewhat significantly before they would fail. And so that's wasted. You're essentially wasting a portion of the life of an object. So we're trying to move away from that. But if you know that an object or material will be taken out of service from before flaws can form, then there really isn't any point in doing inspection at that point. And that this has kind of led to today we have things like aging aircraft inspections. So there are inspections that have to be performed of aircraft of a certain age that don't need to be done on younger or newer aircraft, just because they wouldn't have had those flaws start to form yet. So therefore, NDT looks for unlikely but possible flaws, and that can make it a very frustrating and difficult thing for a lot of people to perform. So over time, that uncertainty accumulates. So the uncertainty in whether flaws would be present in a part or failure probability is going to change over time. And there's a few different elements that come into play. And we create something called a bathtub curve. So this is kind of how that goes together. So first off, when parts are first introduced, when they're new in their life cycle, there always is a certain level of manufacturing defects. And so you have a slightly elevated failure probability very early on in time, whether it's just after a batch is manufactured or in the lifespan where parts are being, production line is being kind of the kinks are worked out, so to speak. There'll be more failures, and then as the manufacturer learns from that, they'll be able to get the defect level down to, they're always going to have an acceptable level, but then things like quality assurance and that kind of thing, we'll try to reduce that as much as possible. The other thing then we have is once parts are put into service, they're going to wear over time. And so you'll have wear failure, and wear failure increases exponentially as you continue on the life of the part. And this is the parts will eventually wear out, and that's usually fairly low for a majority of time. Oftentimes this wear failure, the curve is fairly flat until further over to the right side, but this one just happens to start to come up a little bit earlier. And then there's another kind of layer here called random failures, and these are where there really isn't a good reason that something failed, but it did. Oftentimes it can be attributed to environmental and operating, in addition to wear failure, as certain parts get overheated or overstressed, um, and outside of kind of the normal wear curve. And so, those kind of constitute random failures. It can also be parts just get damaged from uh, handling or from installation or removal, transport. So that all kind of falls in this random failures category. And so you have these three curves, and if we combine them together, if we kind of add them together across time, they create this combined hazard curve, and it makes the shape of kind of a bathtub. And so it shows that there's a relatively higher rate of failure very, very early on, and then it drops fairly quickly, primarily driven by the defects, and then it stays fairly constant until we get later in the life of the part on the right side of the graph. And then it goes up until eventually it hits the top right corner where failure probability is 100%. You expect every part to eventually break down to the point where it's no longer used. Nothing lasts forever. And so we have to define where, NDT is where do we start performing NDT, or what do we have to do? At what point, at what failure probability should we, is it balance the costs of doing NDT with the costs of that failure probability increasing? And so then this leads to NDT being extremely difficult to do. Now, it doesn't mean that the performing the techniques are necessarily difficult, but overall, NDT can be difficult for a few reasons. But when performing NDT, we're often looking for very small flaws, so you have to be very careful at inspecting and be highly skilled in order to do so. However, those small flaws probably aren't there most of the time, by far the majority of the time. We have to have a very high confidence that we will find the flaws that are there when they are present, and also that we don't want to be creating extra work by misidentifying or having false positive results. The high confidence is that when there's a flaw, it'll be found, and when there's no flaw, you won't false positive. You won't say there's a flaw. And then, but then finally, not miss a single flaw that is relevant or over that threshold of criticality. And so NDT must be very reliable to be useful. If it's not reliable and there isn't a high confidence level, then there's always the question, did we actually find what we need to find? And so trying to do all this together can be quite stressful and quite um, difficult in order to be 100% on top of your game all the time, when most of the time you probably aren't going to find anything. So the NDT process has to be designed in this balancing act, where we have those smaller, less dangerous flaws kind of one direction, larger flaws are easier to find. And so NDT is pulled in those two directions, finding smaller flaws as we try to find a smaller and smaller flaw, or if the criticality level gets smaller and smaller, it's also going to decrease our reliability. It'll be easier for someone to miss those small flaws. Looking for larger flaws increases reliability. So because they're easier to find, it's more likely you'll find all of them all the time. And we have to figure out where that balance point is between having an acceptable level of reliability, but not trying to find flaws, not saying we have to find flaws that are so small that we can't reliably find anything. So we've got to make that balance between having an acceptable level of reliability while finding flaws before they become critical. So the question that often comes out and that often comes up is, what is the smallest flaw that you can find? But this is actually a quite terrible question in NDT. And the reason for that, tied to the last slide, is what's more important is we need to know what is the smallest flaw that you can find reliably, that can be found time after time after time, not just what's the smallest we happen to be able to find today, or the smallest flaw you've ever found. Uh, that's kind of maybe some bragging rights, but it doesn't allow you to say, yes, I can find the flaw every time. So we need to know what's the smallest flaw you can find every single time. So they're not equal, and we really don't want to be trying to find the smallest we can find all the time. It's we want to be able to figure out what's the smallest we can find over and over again. And the flip side to that is that that's equal to what is the largest flaw you could possibly miss. So here now we've moved the question to what is the smallest flaw that you can find reliably. We need to know how reliably. But reliability comes at a cost. Higher reliability is more expensive, as is higher confidence, saying that we can, confidence is saying we will find a flaw, every single time. So there's a reliability and confidence trade-off with a given cost. And so the inspector ultimately carries the burden of this. And in order for someone to become certified to perform NDT and be able to provide a level of reliability and confidence, they have to demonstrate their NDT abilities to a level that exceeds the required reliability for a given inspection. So you can't just say, oh, every now and then I can find everything. I have to find more than what I would expect to find every time, or most of the time, so that when I go to inspect actual parts that may or may not be flawed, I can be confident that I'm making the right judgment call. And this leads to probability detection, which is a measurement of this confidence and ability. So probability of detecting a flaw, given that the flaw is present, is the definition of probability detection. And it's typically a function of flaw size. Again, going back to that, bigger flaws are easier to find and smaller flaws are more difficult. But it can also sometimes be a function of other parameters such as location, orientation, um, surface versus subsurface, and other things like that. So we use it as a way to quantify the reliability of a given NDT process, but also a given NDT practitioner. Uh, Two people performing the same test can have slightly different probabilities of detection. One being more skilled or better at detecting than the other, we would need to make sure that anyone who's performing a given inspection in a given method has a high enough probability of detection, or is going to have a high enough probability of detection that they can confidently say they're able to find flaws that are critical, or flaws that are reaching that size of criticality every single time. So the typical measure for POD ties back to that reliability and confidence, and that is if we're looking at the smallest flaw you can reliably find, or again, what the largest flaw you could miss. The industry standard is we want a greater than or equal to 90% probability of detection with a 95% confidence interval, so 95% of the time. Now, a lot of people ask why can't we get it to 100? Well, part of it is there's a human element. The other part of it is we have to take that into account. So when we determine our flaw size, oftentimes the flaws we're trying to find at this what's known as an A90-95 probability and confidence interval uh, are we want to, whatever flaw size we're finding consistently at this A90-95 needs to be smaller than the critical size. So that way, in that one in, that 10% chance, or that 5% lack of confidence period, um, that the next time we inspect something, the crack or the flaw will not have grown to the point where it exceeds criticality by the time the next inspection interval comes around. So the way this is tested is by, and to test a given practitioner is to have a set of known flaw samples that need to be found, that are actually found. It's a test of the individual who's performing NDT. So the minimum you have to have, there's kind of there's some statistics behind this that I'm not going to go into in this lecture, but when you calculate it out, you have to have a set of 29 known flaw samples mixed in with any number of non-flaw samples, and an inspector needs to reliably find 29 out of 29 each time that they perform an inspection on that batch. If they do that, then it will allow someone to have an A90-95 or a 90% probability of detection, 95% confidence when you get out into the real world. So there's some key assumptions when we're looking at this for POD. First off is that larger flaws are easier to detect than smaller. The next is we're going to create a POD curve to kind of show where, to figure this out. And so the assumption is the POD curve is S-shaped, and we'll see what this is in a minute here. And with a sufficient size, you would expect that, a flaw of a certain size, you approach a point where you expect the POD to essentially reach 100%. So after a flaw gets up to a certain level, you should be able to find it. If it's a certain size or larger, every single one of those that are that size or larger should not go undetected. And the curve is created as follows. Here, instead of using a set of 29 known flaws, now most of the time you need a set of 60, greater than or equal to 60 known flaws, and then many more non-flawed samples to mix them in with. And an inspector goes through these, and you record with each each flaw, potential flaw site, whether the person performing the inspection got a hit or a miss. What size. And the sample of 16 known flaw sizes, they vary in size as well. So it's not all just one size. It's a mixture of flaw sizes, so we can kind of start to determine where that A9095 falls with given flaw sizes. So the flaw sizes are ranging from basically impossible to find up to very easy to find, sometimes even with visual inspection. And so the flaw size is plotted against the hit or miss rate, where flaw size is on the x-axis and hit or miss is a discrete indication at the 0 or 100% mark. And then a S-curve is fit to the hit, miss, and the hits and misses, and allows you to find a confidence interval or confidence limits for that S-curve. So here's what one of those graphs looks like. So you can see here across the bottom are flaw sizes. In this case, the flaws ranged in size from just above about a quarter of a millimeter up to roughly 8.5 millimeters. And so here, if a flaw was discovered, it's plotted up near the 100% line. And if a flaw was not discovered, it's plotted down near the bottom 0% line. These plot points in this case have been scattered just slightly up or down just to help make them a little bit more visible, but essentially they're all either 0 or 100%. And then here you can see where the confidence line, which is the solid line, has been drawn between them. So here is the smallest flaw actually found. In this case, it's somewhere just about 1.25 millimeters, roughly 1.25. Here are the large and easy to find flaws. So you can see is if you get past about just over 2.5 millimeters, every single flaw was found, but the largest ones were upwards of 8.5 millimeters. The very small flaws are nearly impossible. You can see anything below about a little over 1 millimeter was missed. So we have very small flaws that are impossible to find. That's okay. In a case like this, we're looking at what could our max acceptable flaw size be. Here's our largest flaw miss. Our largest flaw that was missed was just a hair over 2.5 millimeters. And so with those points, you can create something that is called a best estimate capability line. So it starts down at the 0 probability detection in the bottom left corner, and then it comes up and then it rises very quickly in that transition where it goes from missing flaws to finding flaws. In this case, that range from about 1.5 to just over 2.5 millimeters, maybe 3 millimeters. And then it goes up and traces along that 100% line. So that's the best estimate capability line, but we know being humans, we can't always, humans will not always perform at their best. So then we have to create that confidence interval, and that's where that 95% is. So 95% is that high confidence capability line. And so this line, this dashed line on the bottom is at 95% of the height. It basically is taking that best estimate capability line and kind of shifting it, sliding it down by 5%, taking each point along that line and shifting them down by 5% to get that 95% high confidence capability line. So we say anything along there, flaw sizes, if you want to, you can find the 90% probability of detection there, and where that intersects that 95%, that high confidence capability line, dropping a line straight down. So we start here with our 90% PoD, and we go across to that 95% capability, high confidence capability line. And taking that straight down here, you get about 3.75 millimeters as our high confidence. So, even though in this case, the individual found flaws, quite a few flaws that were less than 3.75 millimeters, what we're saying is we can't say we will accurately find every flaw or even 95% of flaws that are less than 3.75 millimeters, even though In actuality, the largest flaw that was missed is down only around 2.5 millimeters. But this is that we have to show we're better than what the minimum is, what's needed uh, for an inspection to be acceptable. And so there's that 3.75 millimeter for the specific part right there along the x-axis. Now, so the key PoD takeaways then are that A9095 is a bit larger than the largest flaw missed during validation. If I go back, you can see 3.75 in this case is almost 1.25 millimeters larger than the largest flaw that was missed. So it's a bit larger than the largest flaw missed during validation. With the understanding that, again, those very, very small flaws are probably okay. They're small enough that they're not at risk of causing a critical failure. But missing even a single larger flaw is highly likely or can cause a disaster. And so the critical flaw size for a given test object, that oftentimes has to be determined by engineers, and specifically engineers and material scientists. So that's where that number will come from. Then we have to figure out what's the, through the experimentation, what is the inspection, system look like so we can get that A9095. Okay. So what, here, just kind of to summarize, missing very small flaws is okay as long as they're smaller than the critical size for a given test object. Missing even a single larger flaw can cause a disaster. By single larger, I mean larger than the critical flaw size or larger for a given test object. Okay. And then we get into the point where now we start having cases where people find the small flaws but miss larger flaws. And this comes from the flaw variations that flaws in practice are not standards. We have standards that are available for calibration, setting up equipment, where we know that there's going to be an indication, we know relatively how big it is, but flaws are not standard. Actual in-service parts are not standards. And so that leads to some systematic problems too, as well, we can have, where things like incorrect probes or equipment that don't fit the test object area are being inspected. This is particularly the case if you have to do profiles of, think of like a wheel seat area or something like that, where, maybe you need some kind of a specially shaped probe in order to get into an area. Human inconsistency is probably the biggest failure at this. It's as rare but serious, and that is, sorry, that inconsistency is different abilities. The next one is the most serious focus, is looking for the smaller flaws, but kind of not seeing the larger flaws in the surroundings or getting almost tunnel vision, and which can lead to complacency. So the way we can get around this is look for larger flaws first. Before you break out the NDT, make sure you complete a detailed visual inspection. Even once you do the detailed visual inspection, kind of try to hopefully understand what it is you're looking for. And then look for, again, larger flaws. First, one, because we don't want to look past them, but two, if there's a larger flaw present that would make the part unairworthy, there is no point in spending the additional time and money to look for smaller flaws. So this all ends up becoming there's an NDT reliability paradox that comes from all this. And that is a focus on finding smaller flaws has, in fact, in many cases, reduced reliability and increase the risk of missing those larger flaws if people are too focused on the small details. So oftentimes what people do in order to kind of try to make sure they maintain that probability detection and confidence level, and also to make sure that they don't miss anything, is you start having sometimes people erring on the side of caution, but this isn't always a good thing. So making false calls or cautionary calls that maybe end up not being something that needs to be changed doesn't necessarily improve probability detection. In fact, experimentally, experiments have shown there is no correlation between false call rate and probability of detection. So false calls mainly are going to take place at the smallest end of a given indication range. That's where it's the most difficult to maintain that reliability, again, because reliability goes down as the flaw size that we're looking for goes down. And so where misses, the benefit though, or the advantage though, is that this is where misses have the least potential to cause unexpected failure. So that becomes an argument to, not err on the side of caution or not make false calls, just because, if it's so small that it's causing a high likelihood of false cause, it's also probably so small that it has a very low risk to the equipment or to the people traveling or operating that equipment. The other part of this is that experience is no guarantee. There is a certain amount of experience and hands-on training and ongoing performance of different NDT, NDE, NDI methods. But just because someone has been doing an NDT method for 30 years doesn't necessarily make them any more capable than someone who just learned how to do it a week ago and has been doing it. So usually people do not know or see what they miss. And so without having that feedback loop, it's very hard for inspectors to get feedback on what they missed and then be able to learn from that feedback. And so this is a big part of why experience doesn't necessarily improve reliability, because someone may have been doing NDT for 30 years, but never gotten specific feedback over the course of those 30 years, unless somebody else came behind them and did the same inspections, which is very rare because of the cost. So often people who are new to the NDT have good focus. They're excited to be performing something new. They're excited to be taking on more responsibility. They're new to the industry, and it's interesting and something maybe different than what they had been doing. And so they tend to have a high focus and have good results. Not saying a highly experienced person isn't fully capable of what somebody that's fairly new is, but they also, someone who's new hasn't been, potentially dealing with some of the burnout that comes from being in the industry for a long period of time. And then, so then many people who have performed NDT over a period of time become complacent. Just a big part of that is because the vast majority of the time you don't find anything performing NDT, and so you don't want to get so complacent with it. It's like, oh, every time I do this test or every time I do this inspection, I don't find anything. I haven't found it 99 or 999 other times. What makes you think that this time be different? And so people often do start to get complacent and just signing, pencil whipping stuff and not doing a thorough inspection, and that can become very, very dangerous, because then you will have that one time where it turns out that finding something with NDT was incredibly critical. So ultimately, there's a cost to reliability. Measuring PoD in the first place can be very expensive, as I talked about, needing crack sample kits plus the time to test somebody and graph it out and do those calculations. The biggest thing is getting the samples with the 60 to 70 flaws plus unflawed areas and components in them. It definitely has a high cost. So this is getting much more affordable. There are service providers out there, kind of third parties, that now handle a lot of this stuff. Essentially finding PoD for a given individual in a given location. So the other thing that can be used are virtual flaws. There's some research going on with what kind of virtual flaws can we create that approximate and mimic the real thing to a high enough level where it can provide us confidence that someone actually is able to perform inspection with minimal oversight after being trained on virtual flaws. And so this is all still very underused. It's still very research heavy, but I believe it'll be an area that we'll see kind of the industry moving forward, in order to be able to quantify POD measurement at a lower cost. So conclusions then that come from this is the big one is that reliability is paramount and unreliable NDT is useless, mainly because it, if it's unreliable, it doesn't tell us anything, or if it's unreliable, an even worse case is that it's hiding. If things are being judged airworthy or serviceable when they're not, that can lead to a false sense of security and ultimately accidents or failures in service. But you can't improve this reliability if you can't measure it, and so now you start to have companies like TrueFlaw, who I noted earlier in the presentation, that part of their services are to go around and perform POD measurements and provide back a tangible score for how well an inspector is able to perform an inspection. And that wraps up probability of detection reliability.